Well, now as we come towards the conclusion of this tutorial on eye movements, I do want to take just a few minutes to talk about the circuitry that's responsible for generating saccadic eye movements. Now, I won't go into the circuitry for smooth pursuit. It's quite complex and involves essentially all of our visual and visual motor centers that we know about in the brain. And there's a figure towards the back of chapter 20 in the textbook that will lay all that out for you if you're interested. But rather, I think I'll limit our scope and focus on the upper motor neuronal control of saccadic eye movement. Well, there are essentially two principal parts of the brain that are involved in generating the command signals that are then conveyed into those gaze centers in the reticular formation of the brainstem. And at that level, we can consider that to be the level of our lower motor neurons that are coordinating the output from our alpha motor neurons that actually execute the movement. So I want to back up just a bit and consider the upper motor neuronal control of these saccadic eye movements. And so the two main stations that are relevant for controlling saccades from the perspective of upper motor neurons are the frontal eye fields, which are part of the premotor cortex, and the superior colliculus, which is on the dorsal aspect of the midbrain. Okay, so what these two structures do is that they begin to fire just before the generation of a saccadic eye movement. And that timing suggests that they have a role to play in generating the command signals about what kind of saccade to make, both in terms of the amplitude of the movement as well as the direction. Well, what we find in both the frontal eye field and the superior colliculus is a motor map. Now, this motor map for generating saccadic eye movements is informed by sensory maps that are present in both of these structures, and that sensory map represents locations in the contralateral visual hemifield, such that if one were to record from neurons in the frontal eye field or the superior colliculus, one could define a receptive field that would be present somewhere off in the contralateral visual world. If one were then to stimulate the same site from which you would record, what would happen is that the animal or the person would generate a saccadic eye movement to precisely the location of the receptive field of that column of neurons that were just sampled. So this is illustrated in the following figure concerning the superior colliculus. So what we have over here to the left is an illustration of the superior colliculi. So here's the left colliculus and the right colliculus. And what is shown in the left part of this figure is the sensory map. So there is an indication of the vertical meridian here. So here's the vertical meridian in blue. And in red and black, we have the horizontal meridian extending away from the midline into the right visual field. That is represented here in the left superior colliculus. And then in black, what we have is the horizontal meridian that extends off to the left. And so that horizontal meridian on the left side of the visual midline is represented in the right superior colliculus. And if one were to make a recording from different locations in the left and right superior colliculi, one can define a visual receptive field. And that's what's been done for these sites labeled 1 through 8. And these visual receptive fields are indicated by these white regions in the plot here to the right. So each white region is roughly where the receptive field is located in the visual world for each of the recording sites in the two superior colliculi. Well, if that same site in the superior colliculus is stimulated, what happens is that we would make a saccadic eye movement to the center of that visual receptive field. And this implies that there's some kind of registration between sensory map of the world and the map for saccadic eye movements. Now, one might imagine that this registration of a sensory map and a motor map for movement is simply a direct translation of the sensory frame into a motor frame for moving within that sensory world. But we know that our motor systems work in a more complicated way, that what's encoded is not simply some kind of Cartesian frame for movement, but rather really the intention for the movement, or what we sometimes call the motor error, meaning the movement that's necessary in order to achieve the goal. And in the case of saccades, that goal is to acquire a new fixation target. Well, here's an experiment that illustrates some of these points. And I think it's quite interesting, so I hope you'll hang with me and just think with me about this experimental result for just a few moments. So the experiment involves an awake animal model, a monkey that has an electrode implanted in the superior colliculus. And the monkey's goal is to maintain fixation on a central target. And meanwhile, some kind of light is going to go on, and this we'll call the target light, T, here. And so the monkey is still maintaining fixation here, but it knows that it's going to have to make a saccade to acquire this new target at this location indicated by T. So this would suggest then that the monkey simply needs to look up. Okay, well, here's the experiment. And a very clever experiment done by David Sparks and his colleagues. This experiment involves stimulating a site in the superior colliculus during this hold phase, while the monkey is fixating straight ahead, but now being cued to make an upward eye movement. And stimulation of that site in the colliculus causes a shift in the monkey's actual point of fixation. And so this shift now changes the fixation point to a new target here. And so the question is, well, what's going to happen when the monkey actually makes the saccade to the location of the target? If the motor map is being worked out in sensory coordinates, then one might imagine that the saccade that the monkey actually makes is according to a retinotopic-based framework of simply moving up, because after all, that's where the sensory stimulus was presented to the animal, up along the vertical midline. However, if there's some more complex integration of position of the eyes in the orbit, remembering the location of the visual cue to which a saccade must be made, then perhaps the monkey will actually make a saccade back to the original location of the target T. So what's going to happen? Is the colliculus employing a strategy that simply transposes a retinotopic map into motor output, or is there some more complex kind of integration involved? Well, the result to this experiment was unambiguous. What the monkey did was it made a saccade to the location of the target T, even though its eye position was shifted by this devious experimenter that stimulated a particular site just when the monkey was getting ready to make the saccade that shifted the position. So the monkey's eyes first were driven to a new position by the experimenter, and then the monkey made what we might call a compensatory saccade, bringing its eyes to the location of the remembered target. So this experiment really provided great evidence that the way that saccadic movement is organized in the output layers of the superior colliculus is not by simply receiving a sensory framework in retinotopic coordinates, but rather the output of the superior colliculus reflects a map of motor error. That is, a map of the movement that's necessary to achieve the functional goal, in this case of fixating a remembered target even if the position of the eyes in the orbit had been changed following the acquisition of that target. I'd like to make just a few other points about the superior colliculus before we move on to the frontal eye fields, and that is that the superior colliculus receives input not just from the visual system, but also from the auditory system and from the somatic sensory system. So what the superior colliculus really wants to do is direct our gaze towards a novel stimulus, a stimulus that captures our interest or our attention, not because we decided to look in that direction, but rather because the stimulus presented itself. So that stimulus could be a visual stimulus, it could be a sound that happens to be off in a direction that might cause us to look in that direction. Maybe it's a somatic sensory stimulus. Perhaps you're just lounging outdoors and you feel something crawling across your bare foot. Well, maybe it's an insect, maybe it's your pet dog or whatever, but it's an unexpected stimulus that causes you to look in that direction. So that involves a shift in the direction of gaze with a rotation of the eyes. It may also involve a movement of the head and the neck. And recall there are output pathways from the superior colliculus that are directed down towards the spinal cord. We think that they probably operate through reticulospinal connections, but there may actually be a direct projection from the superior colliculus to the upper cervical segments of the spinal cord that mediates this movement of head and neck that allows us to change our visual fixation from one location to another, being driven by a sensory stimulus.